Welcome to our deep dive into rectifiers in electronics. Rectifiers are fundamental components that play a crucial role in converting alternating current, or AC, into direct current, or DC. This process is essential for powering most electronic devices as they require a steady DC supply to function properly. In this video, we'll explore what rectifiers are, why they matter, and how they fit into the broader world of electronics. Whether you're a student, hobbyist, or just curious about how your gadgets work, understanding rectifiers is a great place to start. Let's begin our journey by looking at the basic concept of rectification and its significance. Rectification is the process of converting AC, which periodically reverses direction, into DC, which flows in only one direction. This is a key step in making electrical energy usable for most electronic circuits. Without rectification, many of the devices we rely on daily, from smartphones to computers, simply wouldn't work. The process involves using special electronic components to block or redirect the flow of current, ensuring it moves in a single, consistent direction. This scene sets the stage for understanding the different types of rectifiers and how they achieve this crucial transformation. Alternating current is the standard form of electricity supplied to homes and businesses because it's easier to transmit over long distances. However, most electronic devices require direct current to operate safely and efficiently. That's where rectifiers come in. They bridge the gap between the power supplied by the grid and the needs of our devices. By converting AC to DC, rectifiers ensure that sensitive electronic components receive the right kind of power, preventing malfunctions and extending device life. This makes rectifiers indispensable in modern electronics. Rectifiers come in several types, each suited for different applications. The main categories are half-wave, full-wave, and bridge rectifiers. Each type uses a unique arrangement of electronic components to achieve rectification, with varying levels of efficiency and complexity. Understanding these types is key to selecting the right rectifier for a given application. In the next scenes, we'll break down each type, explain how they work, and discuss their advantages and disadvantages. Let's start with the simplest form, the half-wave rectifier. Half-wave rectifier is the simplest type of rectifier circuit. It uses a single diode to allow only one half of the AC waveform to pass through, blocking the other half. This means that only the positive or negative portion of the input signal is converted into DC while the other half is lost. While half-wave rectifiers are easy to build and understand, they are not very efficient as they waste half of the input power. However, they are still useful in low-power applications or where simplicity is more important than efficiency. Let's take a closer look at the typical circuit of a half-wave rectifier. The main components are an AC source, a diode, and a load resistor. When the AC voltage is positive, the diode conducts, allowing current to flow through the load. When the AC voltage is negative, the diode blocks the current, resulting in no output. The output is a pulsating DC waveform, which can be further smoothed using additional components. This basic setup is often used in simple power supplies and signal detection circuits. Output of a half-wave rectifier is not a smooth DC voltage, but rather a series of pulses corresponding to the positive half cycles of the AC input. This pulsating nature means that the output still contains a significant amount of AC ripple, which can be problematic for sensitive electronic devices. To improve the quality of the DC output, additional filtering is often required. Despite its limitations, the half-wave rectifier is a great starting point for understanding rectification. Half-wave rectifiers have several drawbacks. They are inefficient as they use only half of the input signal, and the output contains a lot of ripple. This makes them unsuitable for applications that require a stable DC supply. Additionally, the transformer utilization factor is low, and the load receives power only during one half of the AC cycle. For these reasons, half-wave rectifiers are typically used only in low-power or non-critical applications. To overcome the limitations of half-wave rectifiers, engineers developed the full-wave rectifier. This type of rectifier uses both halves of the AC input, resulting in a much more efficient conversion process. Full-wave rectifiers produce a smoother DC output with less ripple, making them ideal for most power supply applications. There are two main types of full-wave rectifiers, center-tapped and bridge. Let's explore how each one works and where they are used. Center-tapped full-wave rectifier uses a transformer with a center-tapped secondary winding and two diodes. During each half cycle of the AC input, one diode conducts while the other blocks, allowing both halves of the waveform to be used. The result is a pulsating DC output with twice the frequency of the input AC. This design is more efficient than the half-wave rectifier and provides better transformer utilization, but it requires a special transformer which can add to the cost and complexity. Bridge rectifier is another popular full-wave rectifier design. It uses four diodes arranged in a bridge configuration, allowing it to convert both halves of the AC input into DC without the need for a center-tap transformer. This makes bridge rectifiers more versatile and easier to implement in many applications. The output is a smoother DC voltage, suitable for powering a wide range of electronic devices. Typical bridge rectifier circuit consists of an AC source, four diodes arranged in a bridge, and a load resistor. During each half cycle of the AC input, two diodes conduct and direct current through the load in the same direction. This results in a full-wave rectified output, with both halves of the AC waveform contributing to the DC output. Bridge rectifiers are widely used in power supplies for their efficiency and simplicity. Output of a full-wave rectifier is much smoother than that of a half-wave rectifier. Both the positive and negative halves of the AC input are used, resulting in a higher average output voltage and reduced ripple. This makes full-wave rectifiers ideal for applications where a stable DC supply is required, such as in most electronic devices and power adapters. Filtering can further improve the quality of the output. Full-wave rectifiers offer several advantages over half-wave designs. They provide higher efficiency, better transformer utilization, and a smoother DC output with less ripple. This makes them suitable for a wide range of applications, from small electronic gadgets to large power supplies. The improved performance comes at the cost of slightly increased circuit complexity, but the benefits far outweigh the drawbacks in most cases. Despite their advantages, full-wave rectifiers are not without limitations. The need for more components such as additional diodes or a center tap transformer can increase cost and complexity. Additionally, while the output is smoother than a half-wave rectifier, it still contains some ripple, which may need further filtering for sensitive applications. Understanding these trade-offs is important when designing power supplies. Diodes are the key components in rectifier circuits. They act as one-way valves, allowing current to flow in only one direction. This property is what enables rectifiers to convert AC to DC. Different types of diodes, such as silicon or Schottky diodes, can be used depending on the application. The choice of diode affects the efficiency, voltage drop, and overall performance of the rectifier circuit. Diode is a semiconductor device that allows current to flow in one direction only. When the voltage across the diode is positive, it conducts and allows current to pass. When the voltage is negative, it blocks the current. This simple behavior is the foundation of all rectifier circuits, making diodes indispensable in electronics. Understanding how diodes work is essential for grasping the operation of rectifiers. Efficiency is a key consideration in rectifier design. It refers to the ratio of DC output power to the total AC input power. Full-wave rectifiers are generally more efficient than half-wave designs, as they use both halves of the AC input. Factors such as diode voltage drop, transformer losses, and circuit layout can all affect efficiency. Maximizing efficiency is important for reducing energy waste and heat generation. Ripple is the residual AC component present in the output of a rectifier. Even after rectification, the output is not perfectly smooth DC but contains fluctuations known as ripple. High ripple can cause problems in sensitive electronic circuits, leading to noise and instability. Reducing ripple is a key goal in rectifier design, often achieved through filtering and regulation. To obtain a smoother DC output, filters are used after the rectifier stage. The most common type is the capacitor filter, which stores charge and releases it when the rectifier output drops, smoothing out the voltage. Inductors and more complex filter circuits can also be used for better performance. Filtering is essential for powering sensitive electronics that require a stable DC supply. Capacitor filter is the simplest and most widely used method for reducing ripple in rectifier circuits. It works by charging up when the rectifier output is high and discharging when it drops, effectively filling in the gaps in the output waveform. The result is a much smoother DC voltage, suitable for most electronic devices. The size of the capacitor determines how well it smooths the output. Inductor filters are another option for smoothing rectifier output. Inductors resist changes in current, which helps to even out fluctuations in the rectified voltage. They are often used in combination with capacitors for even better filtering. Inductor filters are especially useful in high-current applications where capacitors alone may not be sufficient. RC resistor capacitor and LC inductor capacitor filters are commonly used to further smooth the output of rectifiers. RC filters are simple and cost-effective, while LC filters offer better performance for higher power levels. The choice of filter depends on the specific requirements of the application, including the desired level of ripple reduction and the amount of current needed. After filtering, voltage regulators are often used to maintain a constant DC output, regardless of changes in input voltage or load. Regulators can be simple Zener diodes or more complex integrated circuits. They ensure that sensitive electronic devices receive a stable voltage, which is crucial for reliable operation. Voltage regulation is the final step in producing high-quality DC power from an AC source. Rectifiers are used in a wide range of applications, from power supplies for electronic devices to battery charging circuits and radio signal detection. They are found in everything from small gadgets to large industrial equipment. Understanding how rectifiers work helps us appreciate the role they play in making modern technology possible. One of the most common uses of rectifiers is in power supplies. They convert the AC voltage from the wall outlet into the DC voltage required by electronic devices. Power supplies often include rectifiers, filters, and regulators to ensure a clean and stable output. This combination is essential for the safe and reliable operation of computers, televisions, and many other devices. Battery chargers use rectifiers to convert AC from the mains into DC suitable for charging batteries. The rectifier ensures that current flows in the correct direction, preventing damage to the battery. Filtering and regulation are also important to provide a safe and efficient charging process. Rectifiers are found in chargers for phones, laptops, and even electric vehicles. Radio circuits, rectifiers are used for signal detection and demodulation. They convert the alternating radio frequency signals into a form that can be processed by the receiver. This is a different application from power conversion, but it highlights the versatility of rectifiers in electronics. Understanding this role helps us see how rectifiers are used beyond just power supplies. Rectifiers are also used in industrial settings such as electroplating, welding, and motor control. In these applications, large amounts of DC power are required, and rectifiers must be robust and efficient. Specialized rectifier designs are used to handle high currents and voltages, ensuring reliable operation in demanding environments. Renewable energy systems, such as solar and wind power, rectifiers are used to convert the variable AC output from generators into DC for storage or further processing. This is a critical step in integrating renewable energy into the grid or charging batteries. The efficiency and reliability of rectifiers are especially important in these applications. Electric vehicles rely on rectifiers to convert AC from charging stations into DC for battery charging. The rectifier must be efficient and capable of handling high power levels. Advanced rectifier designs help improve charging speed and battery life, making them a key component in the growing field of electric transportation. LED lighting systems often use rectifiers to convert AC mains voltage into DC, which is required for LED operation. The rectifier ensures a steady current, which is important for the longevity and performance of LEDs. Efficient rectification helps reduce energy consumption and heat generation in lighting systems. Audio amplifiers and other equipment use rectifiers to provide the DC power needed for operation. Clean, stable DC is essential for high-quality audio performance, as ripple or noise can introduce unwanted distortion. Rectifiers, along with filtering and regulation, ensure that audio devices deliver the best possible sound. Medical equipment often relies on rectifiers to provide reliable DC power for sensitive instruments. The quality of the rectified output is critical, as even small fluctuations can affect the accuracy and safety of medical devices. High-performance rectifiers and filters are used to meet the stringent requirements of the healthcare industry. Communication systems such as telephone exchanges and data centers use rectifiers to ensure a stable DC supply for their equipment. Reliable power is essential for maintaining uninterrupted communication and data flow. Rectifiers in these systems are designed for high reliability and efficiency, often with backup and redundancy features. Computers and servers require stable DC power for their processors, memory, and storage devices. Rectifiers are a key part of the power supply units in these systems, converting AC from the mains into the required DC voltages. The quality of the rectified power directly affects system stability and performance. Many household appliances, such as televisions, microwaves, and washing machines, use rectifiers to convert AC to DC for their electronic controls. This allows for more precise operation and advanced features. Rectifiers help make modern appliances more efficient and reliable. Security systems, including alarms and surveillance cameras, rely on rectifiers for their power supplies. Stable DC power is essential for continuous operation and reliability. Rectifiers ensure that these systems remain active and responsive, providing peace of mind for users. Industrial automation systems use rectifiers to power sensors, controllers, and actuators. Reliable DC power is crucial for maintaining precise control and automation in manufacturing processes. Rectifiers in these environments are designed for durability and high performance. Telecommunication infrastructure depends on rectifiers to provide uninterrupted DC power for network equipment. High reliability and efficiency are essential to prevent service disruptions. Rectifiers in telecom applications often include monitoring and remote management features for added reliability. Laboratory instruments often require precise and stable DC power for accurate measurements and experiments. Rectifiers are used in power supplies for oscilloscopes, signal generators, and other lab equipment. The quality of the rectified output is critical for obtaining reliable results. Aviation and aerospace systems use rectifiers to provide DC power for navigation, communication, and control systems. These applications demand high reliability and performance, as failures can have serious consequences. Specialized rectifier designs are used to meet the stringent requirements of these industries. Marine vessels use rectifiers to power navigation, communication, and lighting systems. The harsh marine environment requires rectifiers that are robust and resistant to corrosion. Reliable DC power is essential for the safe and efficient operation of ships and boats. As technology advances, rectifiers are becoming more efficient, compact, and reliable. Innovations such as silicon carbide and gallium nitride diodes are enabling higher efficiency and faster switching speeds. These advancements are helping to meet the growing demands of modern electronics, renewable energy, and electric vehicles. Summary: rectifiers are essential components in electronics, enabling the conversion of AC to DC for a wide range of applications. From simple half-wave designs to advanced bridge rectifiers, understanding how they work helps us appreciate the technology behind our everyday devices. As new materials and designs emerge, rectifiers will continue to play a vital role in powering the future of electronics.